Hello everyone, I'm Yi Yuan from Wurzburg University. Here we present IC3 transformation on neural implicit maps for remapping functions. As we all know, scene reconstruction is a normal test scope of the 3D reconstruction application. This work is our one step to explore the possibility of dense online reconstruction on large scenes like kitty geometry that requires loop closing embedded. Such work has several challenges: space efficiency, real-time, and remapping functions. Our work starts with novel 3D reconstruction method diffusion that is based on neural implicit maps. On the right side, you can find here is a map with grids. So for each of the voxel, it contains an implicit feature. For each of the neural implicit, it is basically encoded with local geometries. And during the decoding, together with the feature, sample points will be fed into the decoder to get the distance and uncertainty. So advantage of such a method is that it's really cheap cost on space and still maintains a high quality performance for real-time reconstruction. With diffusion's PRV representation, we get a space and time efficiency. However, remapping has rarely been touched by researchers because there's one challenge problem. So here we can find generally we transform points and then encode it, but it's not efficient to do this during the neural implicit reconstruction. So instead, we have to implement the transformation on encoded features. So on this problem, we provide a solution as following. With the transformation of features, we implement a mapping module that works aside of the localization module. For example, when the post graph changes, the mapping module will trigger the remapping and remove the local implicit maps, transform it, and fuse it back. So how we implement the transformation? Our solution is implement SO3 equivariant encoder. So what is SO3 equivariant encoder? For example, you have a point cloud as input, then your encoded feature is with dimension L times 3. So the transformation, the rotation on the point cloud equivalent to rotation on the feature. Based on the vector neural, we implement such a point encoder. For each of the point normal pair, we encode it to get the feature and then aggregate the local geometry to get the FM for that voxel. Because the mean pooling is still rotation equivalent, so the feature equivalent is maintained. In previous slides, we saw the rotation feature. However, there is also a translation, but we find that because our mapping representation is with neural implicit map, that is a set of local implicit. For each voxel, it contains own center. Thus, the transformation of neural implicit map is designed as this. It will first transform the center and then rotate the features. However, there comes another problem when it was used in the mapping, because transformation center grid do not perfectly fit with global. Thus, on the local map, we linearize the feature of target position to approach approximation. Here we can find, so here is one example. This is why we do not directly weighted average the neighbors, because our representation, PRV representation with sparse voxels. So the direct weighted average will get a mass center here, but not on the target. Then with the approximate Jacobian, because our approximate Jacobian is with the subtraction of features, it still maintains the equivariance. So we can make the previous equation consistent by rewrite the Jacobian like this. Then we implement the interpolation to get a weighted average of the neighbor approximations. After fitting a grid, it comes to this function with the weighted average of features with negative and positive for removal and fusion. So for the experiment, our implementation is run on the Intel NUC computer with CPU i7 U CPU and GTX 2881 Ti GPU. So the training is same as diffusion on ShapeNight dataset. It is for the object. And for testing, we're first benchmark on the SCL, NUIM, and replica dataset with full stream from ORV SLAM 2. So after that, we further explore the whole sequence of the kitty geometry with a post stream from PY ICP SLAM. The metrics we're using are accuracy and completeness. So first on SCL UIM, we we evaluate the completeness and accuracy of the transformation. So the completeness shows how well it was reconstructed compared to the ground truth, because it is an average, it is a mean on all the points of the ground truth point cloud. And accuracy is on the opposite, it is average of all of the points for the prediction. So here we can find the error is around 3 centimeters. So it is already small because our voxel sizing implementation is 10 centimeters with resolution equals to 4. Our method produces similar performance, but when there is a loop at LRKT3, our method shows obvious advantage because here is a long loop. We further evaluate on SOTA optimized based method, IMAP. Our method shows better performance almost on all things, but it is weaker on the complementary and the ratio on certain things. It is because our method does not support the whole completion. But still, our method is good in almost every accuracy and most of the complementness. To further explore the usage, we changed the test scope from indoor RGBD to outdoor later. The result further proves the potential of algorithm for such a campus scale outdoor thing. So in this paper, we propose neural-implicit mapping modules that support remapping for loop closing and bound adjustment. We implement SE3 transformation directly on neural-implicit map via SO3 covariance network that introduce a new way for the reconstruction and the mapping design. Thank you for your attention.